is a non-degenerate, which means that if you take the partial derivatives, they all vanish only at the origin. And it is quasi-homogeneous, which means that for every lambda, W okay, so this was the setup we ended up considering after a few consideration in a few remarks in GIT. And then we found on one side the cohomology. Well, if I forget to say, it's the cohomology of an orbifold, right? So I should write general one cohomology. And the orbifold is a hypersurface inside PW, the weighted projective space in n homogeneous variables. By the way, I'm choosing these weights and degree to be coprime. D is actually the sum of the W's because I'm working under a Calabi-Yau condition. Okay, so what I had this side was another version of Chen-Ruan cohomology, which is just a relative Chen-Ruan cohomology of a very simple stack relative to the so-called Milnor fiber. And okay, so we tried to make this explicit. So let me erase this, please. We tried to make this explicit. For example, let me recall that J is this matrix that we have decided to write in the simple way. And let me just, from now on, write G for the cyclic group of order D, spanned by, generated by J, and now I can write this in the usual way. Wherever I put G as the lower index, I mean the G fixed locus of those spaces. And so that's a cohomology which I'm going to consider shifted by twice the age of G. As I said in the first lecture, this is the way Chen-Ruan cohomology is defined, and there is this -2 which comes from there. And now we even did something more. We gave a formula which allows you to explicitly compute this thing. And it was a formula in terms of a ring obtained as a polynomial ring modded out by a Jacobi ideal. So let's see. Again, G is in G. And then I take, okay, here I want to define a little bit better this subspace. This is a linear subspace whose variables, let's say, spanned by xj for all j belonging to a certain set of indexes. This is just a notation I'm fixing. I'm saying something very simple. I don't want to have, I want fg to keep track of those variables that are trivially acted on by little g. Okay, this is just something I want to do. And then I can write in a simple way this space of G invariant elements, a so-called volume form and then a polynomial ring in the variable xj, or this belonging to this, modulo a Jacobian ideal which is spanned by, Okay. So now we're going to have an exercise showing that in a certain specific case, these two things are isomorphic with bigrading matching. It's good to sort of familiarize with this notation. Okay, so here again, I have this Calabi-Yau side. For simplicity, I'm going to choose W to be x1 power 3, x2 power 3, and x3 power 3. And so the Calabi-Yau side is going to look like an elliptic curve inside P2. So if you, anyway, so this is an elliptic curve, and the Hodge diamond is going to be, well, the trivial, this very simple one. Well, here I have the 1, this fundamental class. And here I have also a one-dimensional space, which you can see as spanned by the class of a point. And here I have two one-dimensional cycles on the elliptic curve. So now I'm going to try and find these 4 generators inside this computation. Okay. Does that make sense? I'm just going to repeat this machinery just to give an example of how it works. So let's see. G belongs to Z3. Okay, it can be 0, 1, and 2. And it actually acts by this representation 1 over 3, 1, 1, 1. Okay? So if G is 0, it acts trivially. And as soon as G is not 0, it acts non-trivially. It doesn't fix, it only fixes the origin. Okay? So there are no variables. As soon as G is different from 0, Fg is empty. Okay, let's start from those things. So yes, I want to start from this minus 0. And then I have, well, then I have all the times, all this wedge product and set of variables and ideals are empty, okay? And I only get one single generator. It's like having C, no variables, okay? So the only thing that is left in there is C, okay? So for those things, I have a generator attached to 1 in Z3, yeah? And the generator attached to 2. And we're going to probably have more troubles for determining the degrees of those things. But as far as determining what they are, the real computation is the one concerning the last summon, the one we set aside, which is the one where G is equal to 0. Okay, there, we are in the opposite situation. Fg is the whole set. This is a kind of simple example in which we don't have mixed situations. And there, I have to consider this thing. And this in this ideal, that's what I find. I mean, I have to rescale it. Okay. So, so what is this thing? Well, let's see. As soon as one variable takes a degree which is higher than 1, then it vanishes. Okay, so that we have very little choice. We can only play with x1, x2, x3, which occur in degree 0 or 1. Okay, there are still a few choices, but recall that you want the Z3 invariant part of this story. So the only thing you're left with are these volume forms which occurs everywhere times 1 and rescaled in all possible ways. Sorry. Direct sum with this monomial times this form So I hope this is clear. If not, please ask any questions. So the first part is concerning G being non-trivial. I just get 2 elements. The second part concerns the case where G is trivial. I get all possible variables. And then when I look for the Z3 invariant part of this, then I only get these 2 elements, spanning the whole thing. So here are my 4 generators. And okay, let me tell you what is the degree of a guy happening there. You can figure it out from this definition. But let's say you have a form, alpha, and you compute the degree in a weighted sense. I mean, you give to x1 the degree w1 over d, x2 the degree wn over d, and then you can just try and read off the way of this formula the degree of the corresponding element in this space. Okay, so this has b degree, which is number of elements of Fg minus the degree of alpha times the degree of alpha, which is rather reassuring, but then I have to take into account the age and I have to subtract 1, 1 just to get this thing. And instead of doing this, I'm going to do this like so. This is just another way to say 1, 1, because the sum of the degrees, the sum of the ways, is equal to the degree. But it's going to be convenient in a minute. Okay. So now I let you check that this guy here corresponds to this thing. Let me take some colors. This guy here corresponds to this thing. And now I'm left with 2 guys here, right? And they should go here and here. Just by counting the b degrees, just find that. Okay, so this was an example computed by hand, and let me tell you what the general statement is. That in these situations, with the above hypothesis on W, you can always show that, and for any G. Oh, I see. Let me pause a second. So what I want to do now is to look at this formula and to realize that this formula makes sense not only for the group G equal to J, but for many other groups. So we sort of moved up to here by a certain GIT setup, but now I'm in a situation in which I'm going to just use this expression to define a cohomology theory which can certainly be defined in a more elegant way, but now I just want you to have a precise definition of it. So yes, for any G which belongs to the group of automorphism of W, what is this group of automorphisms of W? It's a group of diagonal matrices satisfying the following condition. You see, inside this group there is certainly one of those groups is certainly this one, which preserves W, just because this group is the diagonal generated by the diagonal matrix, where I have a dth root of unity power W1 power Wn. So it certainly yields 1 when I pull out my lambda power d, okay? Okay, so I take this and I require that J is inside, and or I don't even do that. Sorry, this is kind of unnatural. And then I define something that has been defined by Fan, Jarvis, and Rowan in a paper starting this whole story, and which is attached to W and G, and is defined by this. You see, this definition makes sense even when G is trivial. So you have done something. I mean, just by following the GIT story, you have set up some object that didn't exist before, or they have set up some object that didn't exist before, and that is very useful for computing the cohomology of Calabi-Yau varieties. So I can erase the example maybe. And okay, so you may actually wonder if we have a theorem saying that these two things are always isomorphic, and we do. We also have a theorem when the group is G, so let me state it. W and G as above, with G containing J. I want to do that. Otherwise, my theorem doesn't make sense. All what I said so far makes sense, but now the theorem will set an isomorphism between this bigraded vector space and the Chen-Rowan cohomology. It's an isomorphism with which respect the bigrading. And what I'm doing, I'm omitting C everywhere. This is all cohomology with complex coefficients. And what I'm doing is modding out the hypersurface XW by this guy. That's why I needed J to be there. Okay, so look at what I have here. Well, under the condition that Wj add up to D. This is the condition that ensures me that I have a Calabi-Yau. Okay? So what this theorem does for you is to place the problem in this column instead of this. And as I said, you have much advantage to use this definition, because then you have all those theorems that I mentioned yesterday, which are called the Thom-Sebastiani type of formulae, that actually allow you to decompose expressions like this in smaller bits. And the hope is that this is going to happen also in quantum theories. But let me just sketch how we prove in this way the mirror symmetry statement given in the beginning of the first lecture. Sketch of an application. I don't know, you have PQ of x in the first lecture, and then we had 3 minus PQ of something which we call the dual, and we were wondering if this was really the same isomorphic to that. But going directly from one to the other is a difficult thing to do. Instead, you have isomorphisms to this bigraded vector space. So let me recall that this guy was X mod some group, which we discussed as Z5 power 3. And you see, here I have W, comma J. And here I should find a group such that the reduction modulo J gives precisely that group. Okay? But it is actually rather easy to find that group. And that's SL, because we wanted the determinant to be equal to 1 all the time, intersected with the matrices with values in Z5, 5 by 5. Okay, so those things are still isomorphic, so that's the path that the proof follows. And proving this is a repeated application of Thom-Sebastiani formula, and uses work of Mark Kravitz, which did his thesis in Michigan with Yongbin. So, okay, so that's just an idea of why these things are very useful. So you just place one problem which is indeed difficult somewhere else where you can actually solve it. So now just a schema that we want to follow is the same, but at the level of quantum cohomology. So there is another remark that I should add. And the remark is about this operation of taking the quotient by G. So let me just point out that on the Landau-Ginzburg side, I always have a pair of this form. And when I get to the Calabi-Yau side, I have a quotient. So what I want to stress is that the more you mod out XW, the more here you span out lots of generators. That's because of this definition. Okay? So here you extend your state space, and here you're shrinking your target space. I mean, I just want to stress this because it's something that confuses people sometimes. So when your G becomes smaller, you're just you're just unfolding it, okay? And here you're restricting. So quotienting here becomes expanding the state space, or enlarging the state space. It's just a comment, okay? I mean, may be useful or not. And unfolding, or yes, unfolding, unprojecting if you want, becomes restricting. So to speak. I mean, it's just a hint which is maybe useful to follow the rest of the talk. Okay. So now I have all things set up to introduce this quantum theory, which Fan, Jarvis, and Rouen have defined and is commonly referred to as Fan-Jarvis-Rouen-Witten theory. And so as a first step, I'm going to speak about moduli stacks attached to W, my polynomial. Now, I really want to make explicit what this polynomial is. I just need it. I know it's not nice, but so far I haven't understood a better way of telling this story. So let's write a polynomial as a sum of monomials with the coefficients. Gamma I is just a complex coefficient. And now here is the moduli space. And you're going to recognize that the work we did yesterday is going to be extremely useful, because this is what we call the ZL stable curve. So no problem with that. And then I'm going to put line bundles. But not just one. I'm putting n line bundles. How many line bundles? As many as the variables of this polynomial. Okay, so that's the story. Instead of having one line bundle, they have several. And then they ask the following condition. So let's set I running from 1 to S, and for j going from 1 to n. Every time I fix I can take these line bundles and raise them to the mij power. And then I have this new tensor product, which is again a line bundle, and I identify to omega log of my curve. Okay? So that's their moduli space. And if you look carefully at it, and that's an exercise which is nice to work out, this L1 is nothing but something living here, and this Ln is nothing but something living here. Okay, that's a simple thing to work out. So since this is attached to W, it makes sense to denote it like this.
What's L? ULP?
Sorry?
ZL stable curve. What's L?
Oh, sorry, that's great. Thank you. D. Thank you very much. So let me. So as you see, this moduli stack is just made up of the building blocks that we had earlier, and then we just identify within a fiber product of those blocks a substack that is the one we want. Okay, and now the conjectural picture is that the enumerative geometry of Gromov Witten theory, which the enumerative geometry, which is Gromov Witten theory of this guy mod out by the automorphisms should be related, or actually equivalent in some sense, to the enumerative geometry of this guy. Okay? And now here comes the important point to catch, is that this setup applies also when I have any G which contains J and is contains in the automorphism group. Well, you know, you just well, I told you this time I'm projecting. You know, I had a quotient, and then I'm sort of unfolding it. Okay. So when I unfold, I should restrict this guy. So what is the restriction that I'm going to choose? Well, you know, for any such G, there exists a polynomial Z such that G equals the automorphism group of W plus Z. And then the restriction I'm going to consider is the one where I actually take W plus Z like this. This is actually sitting inside our W. Just because by adding terms to this polynomial, I'm imposing more conditions. Okay? This is actually something that should be proven, but it has been proven. It is actually a corollary of work of Mark-Kravitz. And anyway, so this is a sort of minor point. But, okay, natural question here to ask is, what if G is equal to the cyclic group spanned by J? Well, in that case, here I should only have this, right? Because my reduction modulo G yields the identity group. And now here I should get a very, very restricted space. Which one? Well, it turns out there is a nice level curve space sitting inside here. And that's what W is. Why is this sitting inside the WGN? Well, just check that if I give you a level structure, then I can use it to produce a so-called W structure, which is the datum of those things, but a very special one. One is that is obtained by raising to the W1 W first power, Wn power, the same d root. Okay, so that's how they set up their theory. And you know, you can also say that this does not depend on the chosen polynomial, this kind of things. Let's get back to enumerative geometry of this stack. Okay, so far we just have set up a stack, we move it upstairs, and then we do some enumerative geometry of this stack. So whether you like this stack or not, then the actual work that we're going to do on this stack is very interesting because it sort of involves the enumerative geometry of level structure in a way that is interesting from every point of view, even from the point of view of birational geometry of the spaces. And the word virtual class has occurred even in the course of Gavrit Farkas. So believe me that this direction where physicists point out to is actually something that is going to lead us to interesting questions on this moduli of level structures. So enumerative geometry. This is the enumerative geometry supposed to be dual to the Gromov Witten theory. And they realized that so far you may have lost a little bit, or some of you may have no idea really how to define Gromov Witten invariants. So go ahead.
Sorry. Can you say again in one sentence maybe exactly what this conjecture is saying?
Oh, yes. Oh, in fact, I'm going to say it only at the end. So this is this is okay. So believe me, all the intersection theory doing. I didn't mean to state a very precise conjecture. I'm just trying to sketch a picture, and then now I'm going to introduce some intersection numbers, and these intersection numbers are organized in some generating function, and then I will be able to tell you that one generating function comes from the other. But yeah, I'm sorry, I would like to say, and they even would like to say this generating function are the same on the nose. They are, and there are also people who like this because they say, oh, this is not the same stability condition in GIT. I don't know. Anyway, so we're going to establish some really important equivalence between these things. Once you know all the numerical geometry here, you're going to know the same over there. Any other questions? So yes, what I was trying to say is that I have the feeling that we may still need to say very precisely what is Gromov Witten theory for the quintic in genus 0. Let me write it like this. Any quintic threefold in P4, and that's what I'm going to define Gromov Witten theory in genus 0. That's where I'm going to define Gromov Witten theories in genus 0. Okay, so, well, first of all, there were curves, right? And curves were smooth, and then they became singular somewhere. This was our good old M0n. But then they were mapping to the quintic. So let me be a little bit nicer to them. I let them go to P4. But then I will restrict them to curves that actually map to the quintic. The quintic is the vanishing locus of this section to this line bundle O5. Okay? So with all this set of data, which is the moduli space of stable maps to P4 of a certain degree delta, I can define Gromov Witten invariants just like that. Okay? I don't need to evoke virtual classes. It's going to be a very simple definition. Gromov Witten invariants in genus 0 with n markings, degree delta, and let me add Gromov Witten here because in a minute I'm going to add some other people here. Okay, so and okay, I have a product. Oh yes, H goes from 1 to n, and then oh, I forgot to say that these curves are marked, right? So there are n markings. They are there lying inside this scheme theoretic curve this time. So it's a normal curve. And then if I compose markings with the maps, I get so-called evaluation map that have been already mentioned. So evaluation maps pull back classes. And I can also put here psi classes. Okay, so this problem would be very easy. This should be the Gromov Witten theory of P4. Now what I want to compute is the Gromov Witten theory of the quintic. So somewhere in this story, this line bundle should be involved. And that's here. I put the top Chern class of a vector bundle E, which I would like to define here. It is probably part of the story that has been already said by YPD yesterday. This vector bundle is defined as a vector bundle whose fibers are sections of O5 along each fiber of the universal curve. Now, it turns out, usually it doesn't turn out, it is not like that, but it turns out in this case that this operation yields a vector bundle. Okay? In this specific case, you have a locally free sheaf, and you can actually speak about its top Chern class without any problem. So the whole part of the difficulty of setting up this theory in higher genus comes precisely for this fact that you don't have this nice property. Okay, now mimicking what happens there, we're going to set up FGRW theory for W being the sum of these 5 monomials and G being this very simple order 5 representation. Okay, but this time our modular space is what we call WGNJ, which is, as we just noticed, well, let me restrict to genus 0. I may say something in higher genus, but the objective of this lecture is getting you to understand completely the theory in genus 0 and maybe see somewhere how the higher genus theory works. Okay, so am I going too fast?
Handwriting on superscript subscript that equation is
This stuff here.
Yeah.
Okay, you're right. Actually, I realize, for example, that P is some cohomology class that should be specified. So P is just a hyperplane class in H2 P4. First thing. Now, you see, those numbers are really strange, and I thank you for stopping me here, because this notation is something that mathematicians wouldn't have probably come up with. But for us, it would be simpler to say, well, give me n pairs of numbers, A1, Mn, M1, An, Mn, okay? And then I produce an intersection number. But that's the way they write it. They have this letter tau, which is just a placeholder, okay? So that's, forget the tau. If you prefer, write it like this. I mean, this is just about this jargon that YPD was speaking about. Okay, so then what do I do with this data? I take P, I raise it to the mith power. Here I have P, H running from 1 to n, and I pull it back on my space. I have this evaluation map going precisely in that direction. Okay, this is actually a space, so I shouldn't be afraid of funny things happening. Okay, then I also have psi classes that we have spoken many times about. So I can also compute this cup product. And let me put a bracket here. After having computed this cup product, I cap everything against the top Chern class of a vector bundle.
What is pi here?
Pi is the universal curve, and I forgot to say it. So is there anything else I forgot to say? Yeah, please take all the time. There is coffee here for me. I'm sorry about that. Yes. Okay, so is there anything else? Okay, so the Fan-Jarvis-Van Witten theory. And this time, as I said, this is my moduli space. So smooth curves and funny ZL stabilizers everywhere, even on the markings. We already mentioned this. And now, universal curve, which I write with fancy letters because everything is orbital. And, okay, my friend in the microphone has come here. So, what else? Okay, as I told you, there are multiplicities M1, Mn at every marking, and we noted them precisely by little m yesterday, so we should do it again. And yes, they are going to be somewhat related to those things. And now, what else do I need to set up this theory? Of course, this space carries some divisors, which are just defined in the usual way. So I can already start writing my intersection number, maybe. But here I have WG and J. And I should consider it as, let me write it directly as this. And then I already had this notation before. I'm going to specify the multiplicities at the markings. Okay, this is the first notation that I set up for those spaces. And then for h running from 1 to n, I do this. And again, this would be easy to compute, just as before. The problem is that we have to cap it with some virtual class. Just as in every Gromov Witten theory, there is some virtual class, which is some perfect obstruction theory. And let me tell you something more about this. So you see, the moduli space is a moduli space which we already discussed. It has a curve, a line bundle. But then there is a problem which all the information of this moduli space is encoded in this line bundle. And when I do this, i.e., I take the direct image here, this thing is represented by a complex, which again is a length 1 complex with just 2 term and a differential. And so this gives rise to a perfect obstruction theory. And in the most general case in genus G, many people have provided some definition of this virtual class. It started in a different way from the Gromov Witten setup. And it seems that, well, so there are several constructions that are quoted in the notes. And it seems that in this conference, we are going to hear from Jun Lee a construction that brings the construction of this virtual cycle to a somewhat closer formalism than the construction of the virtual cycle in the Gromov Witten theory. So that's what I guess from I get from the abstract and the notes. So, but let's, for example, exploit some nice properties of this cycle. So this is a virtual cycle. Maybe it deserves a vert somewhere. And but believe me, it does things like I said. If I have W as the sum of x1 power 5, I'm sorry, plus dot dot dots x5 5 power 5, then it should be possible to express this virtual cycle in terms of the virtual cycle attached to each monomial. Okay, so then in fact we have there. I don't care what the variables are called. We can produce this virtual cycle by capping 5 times, and that simplifies things in our specific case. And then if I look at the genus 0 case, well, then I really have something nice happening. As we mentioned yesterday, if we place ourselves in this situation in which genus is 0 and mi is greater than 0, then this was this little exercise that was saying that this vanishes and this is locally free. Okay, so that's good news, because it's a somewhat similar situation to this, although it's completely different in the sense that it's R1 p lower star that plays the same role. But then I can say that this is the fivefold product of the top Chern class of R1 p lower star of L dual. Well, dual is just a matter of notations. But we discussed this yesterday. We discussed that in this case we have an expression saying the following. And if you want, okay, this expression was for certain coefficients s, k, that I asked to check. There should be something like k minus 1 factorial k minus 1. Now, if I want the fivefold product, then I should put a 5 here. And then I'm done. Okay, so why this is wonderful news? Because then in genus 0, we can try and compute this theory. Let me just add a remark. So this is a similar story to this thing, where there is a theorem of Faber and Pandaripande, who actually computes the Chern character of this vector bundle. And here there was this theorem of last lecture, and I'm going to say more on how we used it and on a formalism that has been set up by Dmitry Zvonkin and myself. So here are the invariants, actually. They're called like this. TA1, let's call them again M1 dot dot dots TAN MN 0 N, and here I write FGRW. And now, since this makes perfect sense, I don't need to add anything more, right? So I have two perfectly well-defined theories in genus 0. Okay, so what do this theory do, for example? There's going to be a crucial point in this. So first of all, computing those numbers, the conjecture now becomes somewhat slightly more precise. Okay, these numbers can be computed to the ones you know all those numbers, and vice versa. And when I say can be computed, there is still a little bit of a lot of ambiguity on what is the formula relating one to the others, but I'm getting gradually there. So now I think I would like to start unraveling a little bit more this construction and explaining, for example, why this construction can be, these numbers can be computed. And to do so, I have to speak about one thing which is very important, which is cohomological field theory. So both these theories set up a cohomological field theory, and the cohomological field theory at least in genus 0, is a very simple thing. Maybe while erasing everything, I'm thinking of a little remark, if you have no questions. Yeah, go ahead. Is there any direct you want?
No,
Right. Oh yes, a sort of divisor axiom. There is no divisor axiom, as far as I understand, but there is one thing that we gain, which is there is no degree on this side. So there was a delta wandering around here. That's an integer. And here we don't have that delta. So somehow this balances the lack of this hyperplane relation. So that's, yeah. So in the end, as much as here you get a power series which depends on only one parameter, here you're also going to get a power series which depends only on one parameter. Let me make aside, observe aside a remark. You remember on this blackboard at some point there was an isomorphism between this space, which we call the Fan-Jarvis-Witten state space, and the cohomology of the elliptic curve. And now, if you remember, whenever we had classes attached to G such that the fixed locus was empty, or just reduced to the origin, then we were landing to classes which were hyperplane classes. Meaning classes coming from the ambient space. For example, the fundamental class, which is the restriction of the fundamental class from the ambient space, or the point class, okay, which is just 1/3 of the restriction of the hyperplane coming from the ambient space. So there was this, when we set up this correspondence, we were sending every time classes coming from this condition to classes coming from the ambient space. Okay, so there is a correspondence inside the correspondence which exchanges ambient classes to those classes, which are called narrow classes in the literature on this theory. Why are they narrow? Because G fixes nothing. Similarly, every hypersurface has some cohomology classes that do not come from the ambient space. Those are called primitive classes. And these are some other broad classes in which are, you remember, there was this funny expressions looking like this and this. Okay, so this a dichotomy that happens in this theory. Basically, the Landau-Ginzburg-Calabi-Yau correspondence always sets apart fixed ambient classes from primitive classes in this way. Okay, so now notice that what I have done so far is setting up the theory of Gromov Witten only involving ambient classes. My P were classing coming from the hyperplane. And similarly, on this side, I have, without saying it, only used the entries which are corresponding to M1, M2, Mn, which are integer, which I can regard as classes here. So just to spare you some more unpleasant details, I'm going to stick to this perspective. I'm just going to give a presentation of this correspondence sticking to the narrow classes. So now you're going to see a good reason for calling them narrow, which is cohomological field theory. This is a general theory for quantum theories that has been set up by Kontsiewicz and Manin. And FGRW theory fits this framework. And here we're going to see something which is very important. Essentially, the key property is factorization property. Now, recall that every curve with these level structures have a dual graph. So if I get a curve like this, and I put a line bundle in it, then my curve is going to look like, the dual graph is going to look like this. Now I'm placing myself in genus 0. If I have markings here, I should put little legs that remember me that there are markings. So the markings are number 1, 2, 1, 2, 3, 4, 5. Okay, so this is the dual graph, but as I insisted on yesterday, the dual graph is not a naked dual graph, it's a decorated one. It has a multiplicity index, which I called M, and that I have introduced through a systematic discussion of ZL stable curve and their level structures. Now, I'm going to say that to each object like this, I can attach some morphism gluing good things. Okay, so I is going to be the set of elements lying here. So I'll just have a subset. I is a priori a subset. Well, let's put it like this. I1 is here, and I2 is this set of elements. And I1 is this joint from I2, and their union gives the set of elements up to n. So all very elementary. Now I'm going to say that morally one would expect something like this. Here I write 5 minus n, which should be men modulo 5. And then I map straight to R0 and n I1. Okay, so this is what happens for moduli of curves. And in fact, this map does not quite exist, even in genus 0, if we want to really be precise. And as I described in the notes, we should slightly lift this map. And then there exists a map going this way. Look, this map is actually something that occurred in the lecture yesterday. It's SM. We saw it. It was a component of the singular locus. We sort of identified in a big picture here, there was big component. If you want to forget about this, I'm perfectly happy with that. Pretend that there exists this thing, and now it is clearly what I want to do is setting an identity between these two things. Okay, and I can actually prove it, at least in some proof. For, well, we are in genus 0. I'm going to assume that those are all positive and that m is different from 0. And then I'm going to say something about the case in which m is equal to 0. So, proof of this identity. It's not going to escape anymore. So the proof is as follows, right? So what is the picture that we should have in mind? Well, we had a nodal curve. That's where this morphism lands, right? It all goes into nodal curves. It should be some sort of gluing morphisms. You may feel nervous because I told you that it doesn't exist, but now we're in this, we just dream that it exists, so it's not such a wild dream. And now we are in this, with this family of nodal curves on a base. Actually, the base has there is a copy of the base lying right at the node. You know, where those two components meet. There is a copy of the base scheme. So now we are studying this situation, in which we still have B, just the same thing, but now we have normalized. And yes, so then we are inside here. This is an object of this orbifold. Okay, we are just specifying a locus inside this orbifold, and here we have L1 on this, L2 on this. Okay, so now the idea is the following: you just take L and you pull it back on here, and then you push it forward. So this is not actually a completely trivial operation, because what you get is something in which L injects but has a kernel, which is the restriction to the node. Or if you allow me to say that, since I have identified B with this red locus, the restriction to B. So I'm just identifying the node with B. There is no cheating here. This is the node. And now I'm studying this sequence. Which is going to be a direct image now when I push forward this thing that lives on this node, I push it forward on B. I'm just getting back my L restricted to B. Okay, there is just an identity here. So I can rewrite this. Okay, so now what happens here is that, as I said, under this hypothesis, this vanishes. Now there is something more that happens which is worth checking, and you can do that. It follows from the fact that m is different from 0. This also vanish, both of those. Because again, I sort of iterate the procedure, and I consider L as a level structure on each of these new curves, and things work fine. And then I'm just about to have a comparison between this vector bundle and this vector bundle, which is just what I want, right? Because the top Chern class of this vector bundle is this thing. And this thing is the top Chern class of this other vector bundle. Okay? But now, if I want this to go through, I should kill this guy. So why can I kill this guy? Yeah, I can kill this guy because this guy is trivial. Why? Well, L is a line bundle on a node. But remember, this node is an orbifold node. It has a orbifold structure of order Z, of order L. And this orbifold structure acts on the line bundle in a non-trivial way. Because M, the multiplicity, which comes precisely from this action, recall that the local picture here we set up yesterday was something like this. The way this cyclic group acts on the fiber of the node is non-trivial. And then this vanishes, and I can write that this is the product of these two top-term classes. Well, let me just, as desired. So now you can see that we are in trouble if M is equal to 0. And there should be more work to be done. And that's where, I mean, Witten did all this for us something like 20 years ago. He just went through all this consideration, and then he said, hey, here there should be a vanishing condition somewhere. Now you prove it. And it took many years to set this up correctly, a virtual cycle and the vanishing conditions. And those are things that you can find, I think, partly in the notes, but also in the references that I point you out in this text. So you see, what I want to point out here to you is that this M becomes here some little multiplicity. Oh, I wrote L again. Yongbin will kill me at some point. So I should write 5. So this M yields little multiplicity on one branch and the opposite multiplicity here. And those multiplicities, as long as M is different from 0, are all narrow in the sense that I set up here. And now you see why we like so much all these narrow classes. Because they're so narrow that this line bundle does not survive. It is squeezed at this node. There are no sections surviving. And therefore, we really get a simple equation here. In general, when we don't have these narrow classes and we have to go into these broad classes, the vanishing axioms are going to be very hard to prove. And there we still find lots of hypersurfaces that we don't know how to show that they correspond to the Gromov Witten theory. So these are all open problems in Gromov Witten theory. We actually discovered by going through this argument that there were also statements in the literature in Gromov Witten theory that were not exactly true because they were actually implying something about these broad classes. So we just chase through them. Now we kind of find a sort of nice space where we still things need to be proven, even in genus 0, and they concern these broad classes. So let me just finish with the answer to your question, which is what is now this equivalence. The way I understand it, oh, I see. Yes, I also thought that once you understand this cohomological field theory story, of course you should develop the entire story. Here is just a baby example. But it is not you are not far from understanding, if you understand this picture, what is this cohomological field theory about. Then you should see that this property yields a strategy to compute numbers. I mean, I want to make it clear because maybe some it's not so clear. Suppose you take a nice monomial of this form. Let's call it with a nice letter A. Okay, C1, S1, CH, S, or no, S, M, SM, and then psi classes, A1, M is also a bad letter. I really run out of letters. Q, psi n, AN. Okay, so as you see from the definition that lies behind here, this blackboard, what this enumerative theory is about, ultimately, when you apply this formula with the exponential, is computing these numbers. And now, suppose that you want to set up an algorithm telling you how to deal with a single one of those Chern characters in a certain dimension, then the theorem of growth and decrement, the theorem of the last lecture, so lecture 2, tells you that this guy here splits as a linear combination of terms such as psi n plus 1, I plus 1, A, and then psi h, I h, for h going from 1 to n, and then a sort of a split up computation of intersections like this. Anyway, so this is possible because you have this property. Okay, so this property allows you to go through this, use the previous theorem, and sort of make it work as an algorithm, which ultimately yields a rational number. I'm just sketching this briefly, but it should be. Now, that algorithm seems very hard to. I mean, it's kind of a regular algorithm, always involving this Bernoulli polynomial, etc. But I implemented on a computer using Faber code, and it doesn't actually compute numbers up to a very high rank. But what you can do is to use a machinery called Giventhal quantization that embodies this algorithm. And this has been stated in a theorem by Dimitri and I, as I said, and we now have this algorithm embodied in a symplectic operator whose quantization yields a generating function for those numbers. And now that we have that, those generating function allow us to fulfill this mirror symmetry picture I started from in the first lecture. So the picture had two sides. One was a P1 parametrizing Calabi-Yau orbitals, and around 0 I punctured a neighborhood of 0, and around a punctured neighborhood of infinity there were two restrictions of this four-dimensional vector bundle, which was actually times the puncture disk. And pi was actually the map from this family of Calabi-Yau orbifolds. And then we were producing these vector bundles. One was called V infinity and was equipped with a Gauss-Manin connection. And the other was called the V0 and was also equipped with a Gauss-Manin connection, a flat connection, so that if you are on a contractible set, you can actually trivialize it. But then when you go around these points, as Alessio explained, then you have some non-trivial monodromy. And so here you have a local system of dimension 4. And now, we mentioned already that Giventhal and Lian Liu Yao have a beautiful mirror symmetry theorem saying that the even cohomology of X with its Dubrovin connection can be regarded as a four-dimensional vector space. And computing Gromov Witten theory means, or at least meant for Giventhal, writing down flat sections of this vector bundle on a punctured disk. Okay, when I say flat section, as I said, since we are in a non-contractible space, which is a punctured disk, you should not think of a single-valued function, but you should think that going around a loop, you actually hit upon different values. So what you should regard as sections, the way you should regard these sections is multi-valued functions, sections, taking values in this vector bundle. And now the theorem of Dimitri and myself allowed us to play the similar game here, where we actually take, okay, so here the even cohomology, what is it? It is nothing but the ambient classes. If you think about it, we discussed this already. There is this description of the cohomology. And the even cohomology is nothing but the ambient classes of this hypersurface, whereas the odd cohomology is this 204-dimensional part, which is all the primitive cohomology. So when I restrict to the ambient classes, here I should restrict to the narrow state space of FGRW theory, which means that I should just use the invariants that I have just defined. Okay, and then those invariants allow me to define a connection, which is just as Dubrovin connection defined by deriving in a given direction along tau, and then adding the quantum product between P, which is again a standard class such as the hyperplane class, and here there is a quantum product which is usually, and we will see in future lectures, immediately defined from Gromov Witten theory. So again, computing means finding flat sections, multivalued flat sections with respect to this connection on this puncture disk. So we not only compute those, but we find that they satisfy a differential equation which has been introduced by Alessio yesterday and sort of describes for you this local system. This differential equation is a Picard-Fuchs equation that you can find at, I'm a bit tired to copy down the equation, and probably it's not so important. Okay, so what you find in the fourth section is the Picard-Fuchs equation, which is probably, so page 43, you have a Picard-Fuchs equation on the Calabi-Yau side, and the same Picard-Fuchs equation at the bottom line of page 43 for the Landau-Ginzburg side. So those sections can be regarded as identified to flat section of the same local system. And of course, now I can think of analytically continue one or both of them globally on this space. And then I can wonder whether they are related. And of course they are, because they're flat section, independent flat sections spanning the local system. So there must exist a linear operator transforming one into the other. So the theorem that Youngwin and myself have proven says that there exists a symplectic operator transformation. So a linear map, a matrix with some coefficients, coefficients that we did have no interpretation. So all is analytically continued. Let me write cont and identify to the local system below. And then, okay, so that gives you an idea of what this looks like. And so we found this symplectic transformation, but what does that mean? If you look at the paper we are referring to in this, this paper that we wrote, we have an explicit analytic continuation that gives us these coefficients of this matrix. It looks very much as if they're related to Chern classes and objects which come from the quintic, but we don't really know what they mean. So in the next week, I don't know if Iritani or myself, we're going to explain how the symplectic transformation can be interpreted, and we actually identify it with a cohomological version of Orlov's equivalence, which sets an equivalence between the category of matrix factorization on the Landau-Ginzburg side to the derived category of coherent sheaves on the Calabi-Yau side. Thank you very much.